I'm Vazgen. I'm working at Krisp as a principal machine learning scientist engineer, and also I'm leading the automatic speech recognition team. So today's topic is that how did we build a world-class on-device ASR? Of course, we are not going to go through the all technical details because there are some confidential factors. But we will go through through all processes that we pass through to get some very competitive ASR, and also which works on devices. Okay. So the first question: what is ASR? What is automatic speech recognition? So ASR is a translation of spoken utterances into text. So there are a lot of examples on our daily life of ASR systems. For example, YouTube closed captioning, Siri, Amazon Alexa, and so on. So what makes ASR a very difficult problem? There are four main factors. Let's go through them. The first one is the style of the speech. If you want to build a world-class ASR system, you should support all kinds of styles of speech. For example, conversational speech, read speech, continuous speech, and so on. So the second one is environment. Now, this is a very big challenge to create an ASR system which will work great in a lot of noisy conditions, and also in a very bad in rooms that have very bad room acoustics. Okay, the next one is speaker characteristics. This is also a huge challenge to support, for example, the English accents. So you want to have an ASR system which will support a lot of accents. It started from American English, which kind of not accent, and then Indian English, British, and so on. The next factor is language. If for example, if you are trying to create an ASR system for Armenian, you will have a lack of data. So you will try to do some machine learning stuff to pass that lack of data. But fortunately, in our case, we want to build an automatic speech recognition system for English, and so we have not lack of data. So what is the use case of ASR at Krisp? So the first obvious version is to have a meeting transcript at the end of the meeting, at the end of the call. The next one is to have speech analytics, which is quite a good feature for call centers and also some individuals to have, for example, to count the number of filler words they use, their speech pace, how words they pronounce per minute, and so on. Okay. So is ASR enough to build the first feature, to build the meeting transcript for Krisp? Of course not, because when we are doing ASR, we only taking into account the speeches from the audio stream. But only using audio stream, you can't have information about commas, about full stops, or about question marks, and so on. So not having that punctuation marks, also not having some capital letters will make the readability of your transcript very bad. So you have to have another model, a separate model for punctuation and capitalization. So by saying punctuation, we only mean these three marks: full stop, comma, and question. When we use ASR when we run our ASR on the audio stream, we only get as a punctuation mark apostrophe. For example, we have, and only that cases we support with using only audio stream. Okay, the next challenge, next problem is that if there are a lot of participants of the meeting, for example 5 or more, I don't know, you will have to, for having a readable transcript, you need to know who spoke when. For that, you need to distinguish between speakers, but for that you need to have text-independent features for distinguishing between different speakers. But your ASR model, neural network for ASR, hides almost all features hiding inside the ASR network are text dependent, not text independent. So we need to have another model for answering the question who spoke when. So the another model is speaker diarization. It's called in research community speaker diarization. Okay, the next one that we want to have is word or some sentences timestamp to be able to merge the output of the diarization with our text. We need to have timestamp to have a beautiful transcript, yes, and also this is essential for merging diarization output, speaker IDs with text. Okay. So what are the requirements for meeting transcript? There are a lot of requirements that come from our product team. And the first and the most challenging requirement is on-deviceness. So we want our ASR model to work on device. And more than 95% of ASR systems in the world are working server-side. So it's a big challenge to have a on-device ASR system comparable with other famous APIs or other meeting note companies, and etc. So what on-device brings out? It brings that we should have a small CPU usage, we should have small package size, we should have small memory footprint, and so on. Everything should be small. And also this also comes from our product team, that meeting transcript should be ready after approximately 10 seconds after the meeting. So we can't wait to meeting to end and then start our processing. We need to do processing during the call. Okay. The next requirement is to support accents which are supported by AutoAI. The AutoAI is our main competitor in this field. It's only meeting note company. It's not have another features. The only feature is meeting note and Zoom. And maybe 1 or 2 years ago, Zoom integrated AutoAI to its platform. And also, we need to have better quality than has Auto, or comparable quality. This is also comes from our product team. And it's worth to mention that Auto raised more than $60 million as fundraising, and Krisp raised only less than $20 million. And Auto raised this with only meeting notes system. Okay. So what's the meeting transcript pipeline? At first we had some audio stream. We run ASR on it, and then and then put audio stream into diarization. Then after the ASR, we get non-punctuated text. Then we punctuate and capitalize it, and then we get timestamp with speaker IDs from diarization. And then we merge it with ASR to get final transcript. Here's the full pipeline. Okay, let's go a bit deeper. How our ASR works. So we get the audio stream. We do some preprocessing to get mail spectrogram. And then we use some encoder or acoustic model, which gives us some probability, some logits. Okay, Then we decode it to have a text, and then we do some rescoring to obtain the better candidate. What is the loss function of ASR? There are two main loss functions used in ASR systems: CTC or transducer. So how to choose how to choose between them? Both of them are graph-based loss functions, and what loss function we need to choose. So it depends on your use case. So if you want to have a captioning, captioning or live transcript, maybe you will choose a transducer. If you want to have an offline model, maybe you will choose CTC. But the main difference between them is that the transducer has integrated language model, some kind of language model, which is training in parallel with acoustic model. And CDC don't have such thing. So the main difference is that, and if you want to have a ASR system with very little delay, you definitely should use transducer loss. Okay. So what is rescoring? The first way of rescoring is not doing rescoring. Yes, it's to applying greedy search. This is when we have audio and we run it through our acoustic model, we get some logits for each timestamp. The first way of having the text is taking argmax from each logit and then map it to tokens. The next one is beam search. There are a lot of algorithms for beam search. It's some kind of conditional probability based search. Right? Its output depends on other features too, other logits too. Okay. And another way is beam search plus language model, having another language model, which will help you to have more precise probabilities and then go further. Okay. So what's our data? Currently, we use 7,500 minutes of hours of English speech. This is currently our data for ASR and with variety of accents. Of course, we do a lot of data cleaning, used open source ASR models or something like that, or our models that are not so good enough. We use that models for data cleaning. We have 200 hours of noises to simulate noisy conditions for ASR training. And also we have 5K different room impulse responses to simulate room echo. Okay. We are also performing high pass and low pass filterings to simulate some low quality microphones, because some percent of Krisp user base are using not well microphones, not enough good devices. So we need to do these kind of augmentations. And the next one is codec augmentations. This is for if you want to transcribe the speech that comes to you through the internet. There are some degradations some distortions in the speech because that came from the internet, and we also want to support that kind of scenarios. Okay, and the next one is speed augmentations, and the next and maybe most important one is text normalization. So we have supervised data. Yes, we have audio and we have its labeled text. But for example, if in audio I say I am 20 years old, the text, there are two versions of text. Yes, I am 20 years old, 20 with numbers or 20 with letters. So in this case, we should get rid of numbers and write letters instead of it. So that kind of processing called text normalization, and we have built another ML model for that. And it's not only the ML model; it's also plus finite state transducers, and it's some kind of mix of that. Okay. Okay, how punctuation capitalization works. So we have the output of ASR. Yes, for example, this is output of ASR. Then the neural network for punctuation capitalization. After that, I should have this kind of output, capitalized and punctuated. So the main problem in training punctuation capitalization model is the subjectivity factor. So, for example, if there will be two linguists and you will give them the same text, and you will say them, please punctuate it, then you will get two texts back, and the punctuations will be different, but both of them will be true. So the main problem here is the subjectivity factor. And what's our PC data? We have 300 million sentences in English, punctuated and capitalized. We perform a lot of data cleaning. In this case, also. And we perform ASR-based augmentations. Why? Because punctuation capitalization should work on the top of ASR, and the output of ASR is some kind of distorted. So we need to simulate the distortions when training punctuation capitalization. Okay. How speaker diarization works? Here is a pipeline for speaker diarization. We have input speech. We perform it voice active detection, also created by us to have a segment where was the human speech. Then after getting the segments, we extract embeddings. It's another neural network which extracts embeddings from the audio stream. And then after having all the embeddings which we are having during the call, after end of the call, we are doing clustering and getting all the information about speaker IDs. Okay. Speaker diarization data. Data is quite small currently. It's almost 5,000 hours of speech with 20K plus speakers. But currently we are working. This is of course not small data, but it's small in comparing with ASR data. Of course, we are doing a lot of data cleaning, and currently we are working on enlarging our data of speaker diarization. And of course, we are performing the same augmentations as we perform in ASR in the ASR case. Okay. Test data. So how to test our automatic speech recognition system? How to test our meeting transcript? So you should start from prioritizing your use cases. The first use case is American English, to support ASR in American English. So we collect approximately 20 hours of American English data, the data from different meetings. Yes, it includes different meetings. And then we perform fixed augmentations, augmentations with noise on it, with 0 dB, 5 dB, and 10 dB. 0 dB means that while mixing voice and noise, we scale noise to have the same energy as voice, and then mix them. 5 dB means that noise energy is lower than voice energy, and 10 dB is much lower, and so on. And of course, we are performing also fixed augmentations with room impulse responses to simulate, of course, room echo. Also, we use another dataset, which is a very famous dataset in ASR community. There is our competitor, RevAI. RevAI, it's their own dataset. And why we use this? Why we use this data? Because our main sampling rate of audios is 60,000 hertz. But when you have low quality microphones, the bandwidth of the spectrogram of audio is going very lower. So this is a very real data of phone calls, where microphones are very bad. This is very bad data. So because of that, for example, Google video model word error rate on this data is approximately 17%. Okay. And also we collected custom dataset for 15 different accents, and this list of accents came us from our product team. For example, for South American, British, Indian, and so on, Australian, and so on. Okay. Metrics. Let's talk about metrics for benchmarking our ASR quality. We use word error rate. For punctuation capitalization, we use F1 score, precision recall, and for speaker diarization, we use diarization error rate and word diarization error rate. Here are our ASR results. There are word error rates on our custom collected data for American English. Here's the word error rates for our current model and for Otter's current model. We can see that in all of cases we are beating Otter currently, And let's mention that author works server side, but we are working on device. On device. Okay. The next one also of course, our main computer is author, but we are doing overall the computer evaluations to understand how ASR works on the whole research community. We test Google, Amazon, Microsoft, and so on. So in our custom collected data, we beat them all except Amazon. And currently you can see that in these two scenarios, Amazon's word error rate is better than us. These scenarios are in the case where this is the case when the noise level is much higher. And currently we are working on this to beat in these cases too. Okay. Speaker diarization results. We are working on speaker diarization for I think for 2 months. 2 months, and we have not yet a detailed benchmarking. Only benchmark that I can now share with you is this, only our custom collected American English data set. This is without any noise and reverberation conditions. We beat author in this case too. Great. Okay. So what about package size? So currently we have 4 models, 4 or 5 models is in our package. Let's go over them. For acoustic model, our model size is 52 megabytes. For language model, 59 megabytes. For punctuation and capitalization model, 43 megabytes. And for speaker diarization, 44 megabytes. Also, we have our voice-active detection, which is kind of 1 or 2 megabytes. So overall, the package size of ASR is less than 200 megabytes. And with this, with small CPU usage, working only with one thread and consuming less than 15% of the thread, we are beating author now. So the team that creates this technology over this 1 year, we worked only 1 year to creating these all technologies, and here is our team to 8 talented people of Krisp. Okay, so what's coming next? The first one that we are currently working on it is to improve our ASR in noisy conditions and improve our current diarization model to have chapter separation based on topics, to have a meeting summarization, for example, to summarize 2 hours of meeting for 5 sentences, for example. CPU usage optimizations, and maybe in the not early feature, we will start to work on personal ASR. What's personal ASR? It's if I have dedicated ASR system, then it transcribes only my voice. If it sees someone else's voice, it's not doing transcription. This is personal ASR. So I guess that's it. Thank you. Question?
Thank you very much, Vazgen, John.
First question is introduction question. Do you also infer your models on mobile devices?
No. We are only building it on Mac devices or on Windows devices, and that's all count.
And if we speak about Mac device, you said that you infer models only on CPU, but
yes.
They're thinking about on GPU or even neural units or something.
It's not it's great question, yes, but that job is not in our side. We have in Krisp, we have other SDK team who is working to optimize the model created by us, and they are working to accelerate inference using neural engines, using the new M1 processors or something like that. It's not on our side. Okay.
What technology is being used for real-time analyzation of Krisp?
Analyzation of what?
A signal of incoming data.
Huh? Machine learning. If you are talking to noise cancellation of voice cancellation, it's being done in real time. If you are talking about ASR, it's not done real time. We don't have captioning here.
So when you normally work with audio, you get spectrogram, and spectrogram should normally be fixed size to fit to some fixed.
No. It's not fixed size.
Layer, no?
No. It's not a fixed size.
Dynamic scaling.
So it depends your neural network. You should avoid to use some dense layers in the end of the your network. And if you avoid that, during training, you can pad your data with zeros, and then mask your loss function. And then you will have only this part to have trained.
You genuinely chunk large audio to some chunks.
Yes, through some chunks, the maximum size is approximately 20 seconds. The minimum size is 1 or 2 seconds. So that kind.
Krisp has one of the best noise cancellation models, right? And ASR works on top of these models or separate?
It's a great question. So currently we are working to improve our ASR in noisy conditions. And when I say these benchmarks are done without noise cancellation. So currently our noise cancellation have some distortions that are not hearable with ears, but it distorted audio for ASR systems. So if you apply noise cancellation, then we apply our ASR system, we have the degradation of order error rate. And currently we are working on training on top of the noise cancellation. So we took our noise cancellation, put it in our training pipeline, and we are training on top of it currently. And already we have some improvements, but it's not finished yet.
Do you have competitors among text giants, or you are the only one playing against?
I said the most biggest competitor for us is Otter AI, who said I said that they raised more than $60 million only having that technology, and only on that technology we are working with 8 people, and only with that technology also working server side, they have managed to raise $60 million, and Krisp currently raised only less than $20 million. So it's a big opportunity for Krisp. So.
Since you're on the slide, how did you go about collecting the data on Otter?
Data on what?
The error rates.
Otter has API, so we can submit our test data to them and getting back text, and then compute order error rates.
So you use their current product?
Yes. We use their API, which is not free.
But it seems that your metrics were measured with your data set that you were also using for training your models.
No. It's only test data set. It's only used in tests.
I mean, it's not the numbers from the articles or something like that.
No. It's a custom collected data for our use cases. Of course, we use also some famous data set as LibriSpeech or something like that. But our main use case is conversational speech. Main use case is meeting, and the only open source data set that gets into that use case is Earnings 21 dataset. But Earnings 21 dataset has low sampling rate, so we have to collect our data. So
you said that you tried Google's visual model, right?
yes.
Did you try other models like Rescoring or?
We tried their APIs, I think, for 6 months ago, I guess, and their best model was video model, so we don't try anything else. So their best model was.
What were the results on the problem you said with local benchmark?
Okay. If I'm not mistaken, on Earnings 21 dataset, our border rate was, David will help me. So 12% border rate. Others is some kind of 14, maybe. Google was 17. 17 in Amazon. Amazon maybe 11. Yes, Amazon because this it's not a maybe it's not a use case for Amazon. Yes, Amazon is working on ASR for his Alexa devices, so it's not a use case to have low bandwidth audios.
Okay. Thank you for your presentation. I was wondering how expensive is the training procedure?
It's a good question. Currently, we our one experiment spends, I think, 2 weeks or more than 2 weeks, and also one epoch running on 75,000 of hours of speech is some kind of 29 hours. 29 hours is one epoch time. On 29 hours on 8 A100 GPUs. Yes. So we are training on 8 A100 GPUs, and one epoch time is 29 hours. And so our ASR system listens 75,000 hours speech on only 29 hours.
Yeah, last question for me.
Do you have any idea of what the unique perception is of per error rate? So I imagine if you have one that has 6.8% error rate and the other one has 6.3, I wouldn't notice that one is better than the other. Do you know how big the difference needs to be?
If the word error rate, for example, for me, if the word error rate is bigger than 0.5, then I notice it. But if the word error rate is 0.1 or 0.2, I didn't notice it. So.
Let me also ask one small question regarding the compactness. So what strategies do you use and how you overcome this trade-off between compactness and quality?
Thank you. For compactness, the one biggest thing that we use is quantization to have compact package size, and we perform quantization almost all our models that were 1 minute here. We perform the quantization on acoustic model, on language model, on speaker diarization model, and not yet on punctuation model. So the main thing to get smaller model is quantization for us. And it's post-training quantization, not during training quantizations.
Okay, so thank you very much.
Thank you too.